Welcome. In this part, let's look at a few questions related to MOSFETs. Let's look at the next question. A germanium transistor was built using a 10 nanometer zirconium dioxide dielectric deposited on P germanium, followed by a 100 nanometer tantalum nitride metal gate. The resistivity of the substrate was 0.5 ohm centimeter. Tantalum nitride has a work function of 4.9 electron volts, and the K of the dielectric can be assumed to be 25. For doped germanium, mu P is given by 2000 divided by 1 plus Na by 10 power 17, where Na is in centimeter minus 3. A. What is the EOT or the equivalent oxide thickness of the gate stack used? B. What is the long channel Vt of the above transistor? Ni is 2e13 per centimeter cube. The electron affinity is 4.0 electron volt, and the Eg of germanium is 0.66 electron volts. A TEM was done on the stack, and it was found to be made up of 9 nanometer zirconium dioxide and 1 nanometer of germanium oxide near the channel interface. If the K of the germanium oxide is assumed to be same as that of silicon dioxide, what is the expected Vt of the transistor then? What about the EOT? Qualitatively, plot the CV of the MOSFET with the source drain floating and the voltage applied between the gate and substrate for the two cases on the same graph by first calculating the EOT, right? So the EOT is the equivalent oxide thickness of zirconium dioxide. So in other words, capacitively, how does 10 nanometers of zirconium dioxide look compared to silicon dioxide, right? So if I were to think about zirconium dioxide, 10 nanometers of zirconium dioxide with a dielectric constant of 25 should be equal to the same in terms of oxide, and so this is 1.56 nanometers, right? So this is the equivalent oxide thickness. In that, the capacitance between 10 nanometer zirconium oxide is going to be the same as the capacitance between 1.56 nanometers of silicon dioxide. And the oxide capacitance in this case can be written by epsilon ox by Tox. If I use the oxide, silicon dioxide, I'm going to use 3.1 into 8.85 in 10 power minus 14 divided by 1.56 into 10 power minus 7. This works out to 2.21 microfarad per centimeter squared, right? So that is the effective oxide capacitance of the structure. Now I need to calculate long channel Vt. To calculate long channel Vt, I need to know the doping concentration of the substrate, right? And so what am I given? I'm not given the doping concentration, I'm given the resistivity, which is 0.5 ohm centimeter. So resistivity is 1 by Q times mu n times n, right? Now here what you see is that this mu n is a function of n, so therefore this can be written as 1 by Q into 2000 by 1 plus Na by 10 power 17 into Na, right, by Q. And so this should be equal to 0.5 ohm centimeter. So from this you can calculate Na, and what you get is that Na should be equal to 6.67 into 10 power 15 per centimeter cube, right? So this is the concentration of the p-type germanium. So once I know Na, then the rest of it is relatively easy. So to find phi s is going to be electron affinity of germanium plus Eg by 2 takes me down to Ei plus Kt by Q ln of Na by Ni. Remember, this is p-type germanium, so I'm going below the intrinsic level, and so this is going to be 4 plus 0.33 plus 0.0259 ln of 6.67 into 10 power 15 divided by 2 into 10 power 13, which is 4.48 electron volts, right? So that is the phi s of the system. Phi m, which is the work function of the metal, is given to be 4.9 electron volts. Therefore, phi ms, which is required to calculate Vt in the flat band voltage, is phi m minus phi s, which is 0.42 volts. Right? So this is your phi ms, or the flat band voltage of the system. Right? Now, next thing to calculate Vt, so the Vt is given by phi ms VFB plus 2 phi f plus Qox, which is 2 Q epsilon of germanium into Na into 2 phi f divided by Cox. And when you work this out, right, so here you have 2 phi f is equal to 0.3 volts roughly, and you have Cox, which is 2.21 microfarad per centimeter squared. Everything else is known, so from which you can calculate this. So what you get is this expression is roughly 0.0117 volts. Right? And so for Vt is given by, it's mostly set by phi ms, it's 0.42 plus 0.3 plus 0.0117, right? And this is the case because your Cox is so high. And so this works out to roughly 0.73 volts. Right? So that is the long channel Vt of this device. Now, the third case, in the previous case, we assumed, if you look at the gate oxide, we assumed that this entire thing was zircon dioxide, or that was the intent of the experiment. But what actually ended up happening during the process was it ended up creating something like this, right? So in other words, instead of having 10 nanometer of the high K material, you actually have only 9 nanometer of the high K material and this 1 nanometer of GO2. And since we have said that K of GO2 is equal to K of silicon dioxide is equal to 3.9, so the EOT of the actual stack is actually 1 nanometer coming from the GO2 plus the equivalent of 9 nanometers of zirconium dioxide, right? So this is 1 nanometer plus 9 into 3.9 by 25, and so that works out to 2.404 nanometer, right? So in the previous case we said that the EOT was 1.56, but in reality the EOT, because of that extra 1 nanometer of germanium oxide, the actual EO2 is larger, it's 2.404. Now how did this impact? EOT goes directly into Cox. So initially Cox was 2.21 microfarads. So with this new stack, it's going to be 2.21 to 10 power minus 6 into 1.56 by 2.404, which is going to give you 1.434 microfarad per centimeter squared. Right? And so this is going to change the third factor in your Vt, which is that entire Qs divided by Cox. And the Vt actually doesn't go up much, it goes up to only 0.74 volts. And this happens again because this Cox is so high that small change in Cox is not really impacting Vt much. Right? And so what you see is that the EOT has gone up and the Vt has gone up slightly by only about 0.74 volts. And so what you see, the Vt hasn't changed much. What has changed much definitely is the Cox. So you can see that if I were to plot this on a CV curve, right? Remember, this is p-type germanium, so it's an NMOS. So in reality, if the 10 nanometer zirconium dioxide looks something like this, what's going to happen if this was your 10 nanometer zirconium dioxide, the earlier device? Your actual device might look something like this, right? This part is roughly stays the same. It is a reduction in the accumulation capacitance, which is what is happening in this case. Next question. Consider a silicon MOSFET with the following parameters. L is equal to 0.1 micron, W is 1 micron, Tox is 2.5 nanometers, mu effective is 350 centimeters squared per volt per second, and Vt is 0.9. The maximum supply voltage of this technology is 2.5 volts. A. Calculate the maximum IDS that can flow through this transistor, assuming the long channel MOSFET module. B. Assuming ESAT is 3 into 10 power 4 volt per centimeter, calculate the maximum current including impact of saturation velocity. In silicon, you can assume that VSAT is 10 power 7 centimeters per second. And C, you're asked to make a judgment if A or B is going to be closer to actual silicon and justify your answer. So let's start with the first point. So if you look at the first part, what are you given? You're given Vt is 0.9 volts. You're given W by L is 1 micron divided by 0.1 micron, or W by L is 10. You're given mu effective is 350 centimeters squared per volt second. You're given VDD is 2.5 volts. And Cox, you're given an oxide thickness of 2.5 nanometers. So Cox is 3.9 into 8.85 into 10 power minus 14 divided by 2.5 into 10 power minus 7. This works out to 1.38 microfarad per centimeter squared. That's your Cox, right? And so therefore, if I want to write my ID sat in this case is half mu n Cox W by L, VGS minus VT the whole squared. If I assume VGS is VDD, so it's VDD minus VT the whole squared, right? So which is half into 350 into 1.38 into 10 power minus 6 into 10 into VDD is 2.5, VT is 0.9 the whole squared. And this works out to 6.18 milliamps. So if I use the long channel MOSFET model, my drain current in saturation at the highest gate voltage works out to 6.18 milliamps. Now in the second case, you're asked to consider saturation velocity. So you're given ESAT to be 3 into 10 power 4 volt per centimeter. L in this case, as I said, is 0.1 micron, right? And your VSAT is 10 power 7 centimeter per second, right? So, and the overdrive voltage in this case, VGS minus VT, is 2.5 minus 0.9 or 1.6 volts. Right? So to check how much of this device is actually saturated, what you need to do is look at the parameter ESAT times length. So this ESAT times length is 3 into 10 power 4 into 0.1 into 10 power minus 4, which is 0.3 volts. So it's a very substantial value, right? It's similar on the roughly on the order of VGS VT, right? And so if I look at ID sat, my ID sat is going to be given by W into Cox into VSAT, right? Into VGS minus VT the whole squared divided by VGS minus VT plus ESAT into L, right? This is the drive current of the MOSFET when I assume that velocity saturation is occurring in the device. And so if I substitute the values, my W is 1 micron, 1 into 10 minus 4. My Cox works, 1.38 into 10 power minus 6. VSAT is 10 power 7 into 1.6 the whole square divided by 1.6 plus 0.3, right? And this works out to 1.86 milliamp. So when I use the saturation velocity model, I get my ID sat to be roughly 1.86. Now the third question says, do you expect silicon to follow the long channel square law model, or do you expect the silicon to follow saturation velocity model? And obviously, given this L is 0.1, right, we expect saturation velocity to be dominant. And the way you look at it is you basically compare the value of Vg minus Vt to ESAT L, right? And if those two are comparable to each other, indicates that velocity saturation is important, and therefore that needs to be taken into consideration, right? In case your ESAT L was really high, then you could neglect Vg minus Vt compared to ESAT L, and this equation would boil down to the long channel current. This equation becomes critical when, and in the worst case, when it's purely velocity saturated, this number is very, very small, and you get a relationship where ID sat is proportional to Vg minus Vt, not Vg minus Vt the whole squared. So this saturation velocity, the impact on how critical that is, basically is determined by comparing the values of the overdrive to this ESAT L, and in this case roughly they're of the same order. So you expect your measured silicon to look closer to this 1.86 milliamp rather than this very high value of 6.18 milliamp. Next question. Hafnium dioxide is an attractive replacement for silicon dioxide as a gate dielectric due to its high dielectric constant. Consider a p-channel MOSFET at room temperature. The channel length L is equal to 1 micron, the width W is 10 micron, the effective hole mobility is 150 centimeters squared per volt second, and the substrate doping is 10 power 17 per centimeter cube. Assume that the gate work function is 4.6 electron volts and the silicon electron affinity is 4.05 electron volts. A. Assuming no fixed and mobile charges, what thickness of HFO2 is required to get a VTP of minus half a volt? Second part, find the body effect parameter for this transistor assuming a substrate bias is much larger than 2πf. Body effect parameter gamma is defined by delta Vt is equal to gamma times square root of VSB. C. Find the substrate bias when in saturation the drain current is 200 microamp. The gate is biased such that VGS is 0.7. Assume ideal square law characteristics. And finally in D, what is the maximum VDS that is needed to be applied at the condition C so that the transistor remains in saturation. Right? So first thing is we need to first find the thickness of the hafnium dioxide. In other words, we need to find Cox. First, let's find phi f. Let's do the shebang for the Vt. So phi f, to find phi f, I need to find EF minus EI. EF minus EI is KT by Q ln ND by Ni, which is 0.0259 into ln 10 power 17 by 1.5 into 10 power 10, which works out to 0.407 electron volts. So therefore my phi s, remember this is a p-type silicon, so it's n-type substrate. So phi s is nothing but the electron affinity plus 0.55 minus 0.407, right? In other words, it is 4.193 volts. So this is the work function of the doped silicon. Phi m is given to be 4.6 electron volts. Therefore, phi ms, or the flat band voltage, is 4.6 minus 4.193, which is 0.407 electron volts. Right? So that is roughly your flat band voltage. Right? And so therefore, if I look at Vt, my Vt, this is a P MOSFET, so my Vt is given by phi ms minus 2 phi f. Again, I'm treating phi f to be a positive quantity, minus square root of 2q epsilon s into 2 phi f, right, by Cox. So, and this has to be equal to minus 0.5 volts. So what you're given is 0.407 minus 0.814, that is twice the phi f, right, minus square root of 2 into 1.6 to 10 power minus 19 into 11.8 into 8.85 into 10 power minus 14 into 0.814. Now that's the net charge divided by Cox should be minus 0.5. Right? So in this equation, everything is known except for Cox. So Cox works out to 1.773 microfarad per centimeter squared. And we know that this is hafnium dioxide. So therefore I have 25 into 8.85 into 10 power minus 14 by T hafnium dioxide, right, should be 1.773 into 10 power minus 6. So your T hafnium dioxide is actually 12.476 nanometers. So that's the thickness of the hafnium dioxide needed to get a VT of half a volt. Now once you know that, then, and you know Cox, so now your gamma factor, part B, your gamma factor is given by square root of 2q epsilon s nd by Cox, and that is, substitute the values, it's 0.3103 per volt. Right? So that is your gamma. Now find the substrate bias when saturation. The drain current is 200 microamp. Now let's look at Kp. So Kp of this is given by mu p Cox into W by L. Right? You're given W and L. So W by L is 10. So this is 150 into Cox, which is 1.773 into 10 power minus 6 into 10 by 1, which is 2.66 milliamp per volt squared. So this is the Kp of the device, right? And you're given IDS in saturation to be 200 microamp, right? And the gate bias is given to be 0.7 volts. Therefore, 200 microamp should be half into Kp into VGS minus mod VTP. Again, I'm taking mod of everything, the whole squared. Or this is half into 2.66 milli into zero point 0.7 minus modulus of VTP, the whole square. Right? Or in other words, this gives you your mod VTP should be 0.312 volts. So remember, you have designed this device for a VT of minus half a volt, but you want to get a drain current of 200 at 0.7 volts, which means you need to reduce the VT from 0.5 to 0.312. And that can be done by applying a VSB. So therefore, the delta VT that you needed is equal to 0.5 minus 0.312 or 0.188 volts. And since you calculated gamma to be 0.103 volt minus half, your VSB required is nothing but delta VT by gamma the whole square. Remember, delta VT is gamma square root of VSB. Therefore, the VSB required is delta VT by gamma the whole squared, which is 0.188 by 0.103 the whole squared, or 3.3315 volts, right? So this is the substrate to bias voltage needed, body voltage needed to ensure that I get a VT of 0.312 and hence a substrate bias of a substrate current, drain current of 200 microns. Last question, what is the minimum VDS needed? So the minimum VDS needed is mod VGS minus mod VTP, which is 0.388 volts, right? So VDS has to be less than or equal to minus 0.388 volts to ensure that the transistor is in saturation. Remember, this number depends on the VT, right? So we are using square law model. The VT is modulated by the substrate bias, and because of which your VDS requires to be less than or equal to 0.388 volts. Next question. Shown below is an IV characteristic of an ideal enhancement MOSFET with substrate doping of 10 power 15 per centimeter cube. You can assume Ni is 10 power 10 per centimeter cube at room temperature. Sketch the inversion layer and the depletion region in the MOSFET corresponding to the bias point of Vg equal to Vd equal to 5 volts. Label the doping type in the source, drain and substrate. Determine the threshold voltage of the device. A second ideal device is constructed having identical dimensions and the material parameters except for the oxide thickness. If this device has an oxide twice as thick as the original, what is its threshold voltage? What are the bias voltages and currents when this second device is at the boundary of triode and saturation region? Let's start with the first question. So if you look at the device, you're given basically a substrate concentration of 10 power 15 per centimeter cube. So what are you given? You're given VD sat is 3 volts when VGS is equal to 5 volts. Right? So when VGS is 5 volts, the I saturates at 3 volts. So therefore, this immediately gives you a VT to be 2 volts. Right? VGS minus VT is VD sat, or in other words, your VT is 2 volts. So when VDS is equal to 5 volts and VGS is equal to 5 volts, the transistor is in deep saturation. So in other words, if you think about the saturation, if this is your gate length L, right? This is your N plus, that's your N plus, P substrate, bias. If you look at the depletion region, it's not only pinched off, you also see it creep in to the device, right? Now, obviously, in this case, you don't see a GDS. In other words, you don't see ID increasing. So you can assume that this delta L is much, much smaller than L, but you see that this pinch-off point is going to move in slightly. And if you look at the depletion region of in the MOSFET, it's going to look something like this. Because the drain is at a higher voltage, this is at 5 volts, this is at 0 volts. So you see that the depletion region at the drain is going to be larger than the depletion region at the source. We've already determined the threshold voltage to be 2 volts. Now, ideal MOSFET. Now, third question is what happens if the oxide thickness is doubled? So this is an ideal system. So ideal MOSFET, so my VFP is 0, right? And so your doping concentration, the substrate is going to be 10 power 15 per centimeter cube. Ni is 10 power 10 per centimeter cube. Therefore, your phi f is kT by q ln n by ni, which works out to 0.2982 volts. So now at 2 volts, at Vt is equal to 2 volts, right? You have 2 phi f is equal to Vs. That's the voltage in the substrate. And that is basically 0.2982 into 2, which is 0.5964 volts. Right? Remember, Vt is Vs plus Vox. Right? So we know Vt, we know Vs, which means the Vox when the at threshold is going to be 2 minus 0.5964, which is 1.4036 volts. Right? Now, this is the part of the threshold voltage that is dependent on the oxide thickness. Right? So, and remember, threshold voltage is determined by the doping concentration. Right? So, if my doping concentration is the same, that means that my phi f that is needed for inversion, that 2I phi f remains the same. In other words, the charge in the semiconductor remains the same. So, therefore, if I double the oxide thickness. So if the oxide thickness is doubled, then to support the same charge, I need to apply twice the voltage required, right? Because remember, the charge inversion remains the same because the doping concentration is the same, right? So therefore, for the when the oxide thickness is doubled, my new Vox new is going to be 2 times 1.4036, which is 2.8072 volts, right? This point still remains the same. Vs continues to remain 2 phi f, which is 0.5964. So therefore your Vt new, that is when you double the oxide thickness, the Vt doesn't double, the Vt becomes 2.8072 plus 0.5964. In other words, becomes 3.4036 volts. Right? So the Vt doesn't double, only the part of the Vt, that is the Vox, that is the only thing that's going to double. And the last question is, what are the bias voltage and currents when the second device is at the boundary of triode and saturation at VGS is equal to 5 volts, right? So obviously your currents are going to change, right? Current is going to, ID sat is now going to be given by half mu of Cox W by L into VGS minus Vt nu the whole square. So if everything else remains the same, this part remains the same, what you get is your ID nu divided by 10 milliamps, which is what the current was in the figure in the question, should be proportional to 5 minus this new Vt, 5.306 the whole square, divided by the old version, right, which is 5 minus 2 the whole square. And therefore, what you get therefore is you get your current to be now 1.4 milliamps. Right? So previously from the Vt being 2 volts where you got 10 milliamp of current, when you increase the oxide, the Vt went up. So for the same voltage now, your current is reduced and it's reduced to 1.4 milliamps. Moving to the next question. The following parameters are given for an NMOS process. EOX is 50 nanometers. Substrate doping is 1e16 per centimeter cube. Polysilicon gate doping is 10 power 20 per centimeter cube. and oxide interface fixed charge density is 2 into 10 power 10 per centimeter squared. Calculate the Vt for an unimplanted transistor at room temperature. So just calculate the Vt of the regular transistor. What type and what concentration of impurities must be implanted to achieve a Vt of plus 2 volts and a Vt of minus 2 volts? You can assume that this is a shallow implant right at the surface of the semiconductor. So what we're trying to say is, let's assume that this is a certain semiconductor, right? This is your metal, this is your oxide, right? And there is a certain Vt that is set. So this is, say, it's an NMOS, so there's a certain Vt that is set in the device, right? Now the question is that you can modulate the Vt by applying a sheet charge at the surface, either by applying a positive charge or by applying a negative charge at the surface. And so we need to find what that needs to do. So first part is find the Vt of the unimplanted device, right? So here you're given Tox as 50 nanometers, Na is 10 power 16 per cc, polydoping is 10 power 20 per cc, right? And your interface trap charge density is 2 into 10 power 10 per centimeter squared. So let's start Cox. Let's first find Cox. Cox is epsilon ox by Tox, which is 3.9 into 8.85, 10 power minus 14 by Tox. Tox is 50, so 15 to 10 power minus 7, which is 6.9 into 10 power minus 8 farad per centimeter squared. Now, what is 2πf? 2πf in this case is going to be 2 times kT by Q ln Na by Ni, which is 2 into 0.3473, which is 0.6946 volts. So that's your 2πf, right? Now, to find Vt, I need to find the VFP, I need to find and Vox. Now, to find VFP, I need to know phi ms. Now, here we have said that it's polysilicon doped, it's doped polysilicon is the gate, and is doped n-type. So therefore I can assume that in the poly it's heavily doped, so I can say that its Fermi level is at the conduction band of silicon, right? Because it's degeneratively doped conduction band of silicon, and so therefore my VFB is nothing but phi ms, right, which is nothing but minus Eg by 2 plus phi f. That's because my phi m is sitting at the conduction band, and this is an NMOS process. So my phi m is lower than phi s. So therefore my phi ms is going to be negative. And so if I calculate that, that is going to be minus 1.1 by 2 plus 0.3473, which is minus 0.8973 volts. Remember, again, what am I doing here? We are basically, if you think about your silicon is sitting here. It's a p-type silicon. So p-type silicon is going to have a phi s, which is going to come all the way down, right? Whereas your poly has a phi m, which is only coming to the top. So therefore, this delta is your phi ms, and it's negative, right? Now, at Vt, we calculate the drop. So Vox is again given very simply by 2q epsilon s Na into 2πf by Cox. Again, everything is known in this equation, and so you can get your Cox to be 0.6979 volts. Right? So now if I look at Vt, my Vt is VFB plus 2πf plus Vox minus QF by Cox, right? Because that's going to impact my VFB, and this QF by Cox is nothing but my 1.6 in 10 power minus 19 into the charge density, which is 2 into 10 power 10, divided by Cox, which is 6.9 into 10 power minus 8, and this works out to 0.0463 volts. So this is the change in VFB because of the fixed charge. And so for my Vt is now going to be VFB 0.8973 plus 2πf, which is 0.6946, plus Vox, which is 0.6979, minus QF by Cox, which is minus 0.0463, and that works out to 0.4489 volts. So roughly 0.45 volts is the Vt of the device. So therefore now if I need to make the Vt 2 volts, right? So I need to make, suppose I want to make the Vt 2 volts, that means I need to add or change the VFP in such a way that the VFP increases, right? So therefore I need to add a charge, delta Vt into Cox, right? Because I'm assuming this charge is sitting right at the interface. So in other words, I need to add a charge of Q is equal to delta Vt, which is 2 minus 0.4489, right, into 6.903 into 10 power minus 8. So that is 1.07 into 10 power minus 7 coulombs per centimeter square. Now to increase the Vt, what should this charge be? Now this Vt has to increase, this charge has to increase the VFP. So if it has to increase the VFP means this charge has to be negative, right? So to add this, to make the Vt plus 2, I need to add a negative charge of minus 1.07 into 10 power minus 7. What do I mean by adding a negative charge? That means I need to add more p-type right at the interface so that the locally it looks like a fixed charge, and therefore I can change the Vt of the device. So I can think about adding a local Na density of 1.07 in 10 power minus 7 divided by 1.6 in 10 power minus 19, or 6.6875 in 10 power 11 per centimeter squared, right? So I need to add this amount of doping at the interface to increase the Vt up to 2 volts. Now therefore, to get the Vt down to minus 2 volts, what do I need to do? I need to add a charge which is 2 plus 0.4489, right, into 6.903. So I have to compensate, I have to take it on the other direction. And so therefore I need to add a doping density of this charge divided by Nd. So this doping of 1.056 into 10 power 12 per centimeter squared. So I need to add a doping of 1.06 into 10 power 12 per centimeter squared so as to get the Vt to minus 2 volts, right? And so it's intuitive that if you think about this at the surface, this is again your gate, right? This is your Na. If I want to increase the Vt of the NMOS, if I add more Na at this surface, I'm going to increase the Vt of the device. If I want to reduce the device, I'm going to add more Nd at the surface, and that's going to reduce the Vt of the device. Moving on to the next question. A set of IV characteristics for an NMOS transistor at room temperature are shown for different biasing conditions. Some of the parameters are given as WL is equal to 1, Tox is 34.5 nanometers, 2πf is 0.64. Using the data, find the threshold voltage, the channel electron mobility, and the body effect coefficient. So let's replicate the table here. So I have VGS, VDS, VSB, and I have ID in microamp 4545, 4545, 00, 2.6, 2.6, 256, 441, 144, 256. We are also given W by L is equal to 1, Tox is 34.5 nanometers, and 2πf is 0.64. You're asked to find the Vt of the device, you're asked to find mobility, and you're asked to find gamma. Right? So first thing is, in all cases you see that VGS is equal to VDS. That means that in all these cases the transistor is in saturation because VGD is 0. So therefore I know I can use long channel model. So therefore my IDS at 4 volts gate divided by IDS at 5 volt gate, right? If I take row 1 and row 2, right, without substrate bias, Then I can write this as 4 minus Vt the whole squared by 5 minus Vt the whole squared should be 256 by 441, right? In other words, take square root on both sides. 4 minus Vt by 5 minus Vt should be 0.762. In other words, your Vt is 0.7983 volts. Right? So that's the Vt of the device. Right? Next thing you have to find is mobility. Right? Now Cox we know is given, we know Tox. So Cox is given by epsilon ox by Tox, which is 3.9 into 8.85 to 10 power minus 14 divided by Tox, which is 34.5 into 10 power minus 7, and this works out to 10 power minus 7 farads per centimeter squared. So that's your Cox, right? Now to find mu, I can either use the equation, the 4 volt current or the 5 volt current. So if I use the 4 volt current, I have IDS at 4 volts is half mu n Cox W by L VGS minus Vt the whole squared. Right? In this I know all terms except for mu n. So therefore my mu n is 2 into 256 to 10 power minus 6 divided by 10 power minus 7 into 1 into 4 minus 0.7983 the whole squared, which works out to 499.46 centimeters squared per volt second, or roughly 500 centimeters squared per volt second. That's my mobility, right? Now, again, the last thing you're asked to find is the substrate bias or the body bias factor, body effect coefficient. And if you look at that carefully, that can easily be found by using the same technique as we did for calculating the Vt using these two lines. So that gives you the Vt for this given body substrate bias. And then using the expression for the body coefficient, I can find out the value of gamma. Okay? So similarly, or I can use mu. So either I can do this and do this, or I can, once I know mu and Vt, I can use that to find the Vt of what happens when Vt, when a body bias of 2.6 is applied, right? So if I use the third row, that is when VDS is equal to 4 is equal to VGS, then IDS is 144 microamps, right? Now using the value of mu as 500 centimeters squared per volt second and Vt as 0.7, not Vt, you need to find Vt. So what I can do is using this, I can find what the Vt. So by Vt, when I apply a substrate bias, is given by VGS minus square root of 2ID by mu n Cox W by L. Again, I use the saturation current equation, which is 4 minus square root of 2 into 144 into 10 power minus 6 divided by 499.46 to 10 power minus 7, and W by L is 1. So this works out to 1.599 volts. So this is the Vt at VSB, right? And so what it tells you is when I apply VSB of 2.6 volts, my Vt goes from 0.7983 volts to 1.599 volts. In other words, my delta Vt, or this is my delta Vt. So to find the body coefficient, I know that my delta Vt can be written as gamma into square root of 2 phi f plus VSB minus square root of 2 phi f, right? So I know everything in this equation, so therefore my gamma can be written as delta Vt by square root of 2 phi f plus VSB minus square root of 2 phi f, which is 1.599 minus 0.7983 divided by square root of 0.64 plus 2.6 minus 0.64, which works out to 0.8097 per volt. So your body effect coefficient is 0.8097. So again, by measuring the IV characteristics of the device at specific points, you can calculate or do modeling of the various parameters of the MOSFET. Let's go to the next question. Biases VGS equal to 3 volts and VDS equal to 0 volts are applied to an ideal N-channel MOSFET with a width of 70 micron, an L of 7 micron, mu n of 550 centimeters squared per volt second, a TOX of 50 nanometers and a VT of 1 volt. Making use of square law theory, determine the inversion charge layer at the midpoint and determine the drain conductance at the given bias point. Now, VDS is equal to 0, which means that the inversion charge density, if you think about it, since VDS is 0, the inversion charge density is going to be a constant across the entire surface, and it's going to be given by Cox into Vg minus Vt. So my Qi at L by 2 is very simply Cox times Vgs minus Vt, and Cox is 3.9 into 8.85 into 10 power minus 14. Your TOX is given to be 50 into 10 power minus 7. This is Cox. VGS is 3 volts, right? And VT is 1 volt. So 3 minus 1. So that works out to 1.3806 into 10 power minus 7 coulombs per centimeter squared. So this is the inversion charge density in the middle of the channel. Now in the so this is at VDS equal to 0. So when VDS is equal to 0, the transistor is in linear region. In other words, I have my IDS as mu n Cox W by L into VGS minus VT into VDS, right? So my GDS is nothing but dou IDVS by dou VDS, right? Output conductance, and that is nothing but mu n into Cox into W by L into VGS minus VT. Again, everything is known in this, so I can calculate this to be 550. Cox we just calculated was, or Cox times VGS minus VT we calculated to 1.3806 into 10 power minus 7, and your W by L is 70 by 7. W 70, L is 7. And this works out to 7.5933 into 10 power minus 4 amps per volt, right? So that is your output conductance of the device.